Hello, in this video we will be covering unit vectors. Um, well, not just unit vectors, vectors of all kinds. In Calc 3, this is where we start getting into the 3D space a lot more seriously, more in depth. Calc 1 and Calc 2, we've gotten 2D vectors, a little bit of 3D vectors in Calc 2, but now we're really going to be looking at how they work in space. I've dealt with a little bit with it in physics, probably not a whole lot. Dealt with a lot of in-plane stuff, like Calc 1 and Calc 2, where you just assume everything is in the X, Y plane, and you don't really mess or worry about the Z plane too much. But now that's no longer an assumption we can make. A lot of things are going to be happening in X, Y, and Z directions, which we denote as the I, J, and K direction. I want to start just by going over all the vectors. You don't need to know for the entirety of the course, but you really need to be familiar with them for engineering. So our first vector, these first three vectors are really going to be integral to a lot of what we do in calculus, Calc 3. So I'll just go ahead and get started with that. So our first vector is a position vector, which is denoted as r of t. And I put the little arrow above it because, again, it is a vector. So this is our new x of t. Instead of saying f of x, we denote something as a function r of t, or position, which is going to be equal to three different functions of x, y, and z, where x of t is in the I direction, y of t is in the j direction, and z of t is in the k direction. So these can't all be combined, but whatever is happening in the I direction, whatever that function is, that's x of t. Same thing for the j direction and x or k direction. So these are just individual positions. If you care about just looking at what's happening in the x direction, you can just look at that. If you care about what's happening in the x and y direction, you can do that. If you need all three, you're able to do that. But it will depend depending on what your application is. Do you need to look at whatever or use these as individual vectors or one big vector? It will change, but you need to know what these three I, J, and K functions stand for. They're just position functions for the X, Y, and Z, but you're just looking at it as three different functions. And if you had some particular time given, you get 1 point on the X, the Y, and the Z, so you get an X, Y, Z coordinate. And if you get a map of those or a series of times, you get a line moving in three-dimensional space. All right, so the velocity vector, as you can tell, is going to be the derivative of r of t. So it's going to be dr dt. And then you would have to take the derivative individually for x of t plus dy dt plus dz dt. And that would be your velocity. And acceleration, same thing, is dv dt. And I'm just going to note this real quick. It's also equal to the square root. Actually, I want to say square root. It's also made up of a sub n plus a sub t. And I'll get to those later. So these are the normal and tangential acceleration. And I'll explain how you get those and what they mean or how you draw it a little bit later. Actually, I want to write these with capital letters. In t. There we go. So next one we have is speed. So speed you should be pretty familiar with. It's pretty much how fast is one moving. It's like your speedometer on a car. It doesn't tell you anything about the direction. It's not like a compass in any way. You just know if you're going fast, going slow, or not moving at all. And that's what. And so if you care about just the absolute speed, then we're going to take absolute change of position. Then we're just going to do the absolute value of the velocity. So that's what speed is. And this can also be denoted as ds dt, or the magnitude of ds dt. S is just another way of saying position, so it's just to change the absolute value of the change of position. So which again is still the absolute value of v of t. So, all right. So next we have the tangential unit vector. So this is probably where it's going to be the first thing you're like, oh, okay. It's not difficult, but these are going to be the beginning of all the weird looking equations that kind of make sense when you think about it a little bit more, but you're not really familiar with. So the tangential unit vector is going to be the unit vector of your velocity. So it's going to be v over the magnitude of v. And there's different ways you can write it. You can write it as ds dt over the magnitude of ds dt. But this is I think this is what they tell you. The second one is what they tell you in calculus, but this one I think makes way more sense. So I'd follow that one. But just note that also means the same thing because some other equations will reference ds dt and require you to use ds dt and not as a function, and not, it won't say velocity or magnitude of velocity. You'll see what I mean. So this next one, curvature. So curvature is basically how much is something, like how big is the curve. If it's curving very quickly, that means it has a very small radius about which it's rotating about. Because curvature, which we know is k, is equal to 1 over rho. And rho is the radius of curvature. So if you had some line with so say you're going straight, and then you're going to make a turn where your radius is 5, where this, when that's the distance from where you're at to the center of where you're going to rotate about. That means your curvature is going to be 1 over 5, even though where your radius of curvature is 5. This comes really mainly in handy for the oscillating circle. But they'll still ask you to calculate it in other cases, because you're going to need this for normal acceleration as well. But another way, but you're not giving k or rho, so you can't really get one or the other. But you can get it by doing the derivative of your tangential unit vector. And I should have said what the tangential unit vector looks like. The symbol, it's t hat. So curvature is the absolute value of dt hat ds. So this is where I was talking about with the ds thing. So now we need to break this up into two more. So it's going to be dt hat dt all over ds dt. Be the magnitude of that. Now be your curvature. And you can pretty much just say this is dt hat over dt all over magnitude of velocity. That's another way to denote it. All right, so unit normal vector is going to be n hat. So this time I won't forget it. Is n hat. And this is just a unit normal. This is just a unit vector for the normal velocity. And that's going to be equal to dt hat. So you change the dt hat ds over the magnitude of dt hat ds. Should make more space for that one. I'll be fine. Because I forgot I made more space in this next one. So I'll rewrite that. tt hat ds over ds dt. Oh wait, no, I didn't get that right. Sorry. Magnitude t hat ds. There we go. And then you already calculated the bottom part. So you've already calculated this. This is essentially k. The denominator is essentially k because it's dt at ds. And the dt ds in the numerator is also kind of the same, but instead of being the magnitude, you just want the direction of it. So again, you're going to have to break this up into t hat dt over ds dt. But in this case, since it's not magnitude anymore, this is really velocity. So this is just that top part. I'm going to go ahead and circle. So that's what that top part is that dt hat dt over velocity. While the bottom part is k. So you're really taking this whole entire thing and dividing it by k. I'll do it like that. And I'll circle this. All right. Yeah, so this is probably where it gets the most complicated, starting with the normal vector. Or I guess curvature. Curvature is also pretty complicated in calculating, and they don't give you nearly enough space, which is normal. But the next part is the binormal unit vector. So really, so you have to look at t. So what this is b is equal to your tangential cross your normal. So if you remember from Calc 2, Unit 1 and Unit 2, when we took a cross product of two vectors, we got a vector that was normal to that plane. That's essentially what this binormal unit vector is supposed to be. It is a unit vector that is normal to your t and your n, and normally it's binormal because it's directly in the middle of the two. Well, it's also it's not really. It's binormal because it's on two different sides of it, because it's normal to one side of the plane and then on the other side of the plane. And this is my funny way of remembering this. This is I don't know why, but every time I read this, I think Ben 10, and I don't know if you've even watched the show. I don't even know if you're even that was even on television when you would have watched it. But this is really to help you do the cross product, because this is probably the first time you really start doing cross products. This and statics for the people who are in statics, like 3 majors I think are in statics. Start doing it in other classes that require it. It's pretty much you pretty much need to learn a cross product at least once in your life to do a lot of other math. At least I say once in your first year, and I don't know. It depends on the class. I would say first in your life. So we have this would be I, J, and K. So this is the first row is I, J, and K. So whatever they each have in common, which is the I, J, and K, these are the parts that they're going to separate it. Then you have the T components. So this is T hat X, T hat Y, and T hat Z. So this is the X, Y, and Z component of T. Then you have, I put a vector there instead of n hat. And I also did the same thing there. This would be nx, n hat y, n hat z. And then you do the what's called the determinant, which you probably are some of you are probably familiar with that if you did a determinant in pre-cal with a 2x2, not too bad, but with a 3x3, way different, a little bit harder. And this is like a good summary of what you essentially do is going to be I times T hat Y n hat Z, and you don't have to memorize this. You're going to be able to figure this out as soon as I explain where they all come from. T hat Z n hat Y. So for your I, I'll get a different color out. So for your I component, you are going to essentially block off the bottom row. So the first column, you're not going to look at the first column. You're going to do a cross product between the top left and the bottom right. So that's T, Y, and Z minus the top right, bottom left. So it'd be T hat, T, Y, N, Z minus T, Z, and Y. And it'd be the same deal when we do, I'll do a different color, I'll do it in a darker color. When we do J, I can't even tell. You can kind kind of tell. So for J, you're not going to look at this column here. You're not going to look at the first column. You're going to look at not going to look at the second column. You're going to look at the first column and the third column. So it would be TX and NZ and NX and TZ. So those would be the two you're going to be combining. So for the J term, it's also minus J. That's one of the things you have to memorize, and that's because of you're not doing the change in direction. So it's going to be minus. You're really doing the sign of negative 90 degrees or the cos. There's more in-depth math, and I think if you have statics, they'll explain why that happens. But I'm not going to go do that here. So this one would be T hat X NZ minus T hat Z NX. And the last one, you can probably figure it out. It's going to be plus K. And now we're going to do it with the X and Y components. So it'd be T hat X N hat Y minus T hat Y N hat X. That will be your binomial unit vector. Probably a little bit more, this is a little bit more intense, a little more algebra. I mean, this is a good thing to learn now because you're going to be using it in statics, a lot of other courses where you need to use physics stuff. I've had to use it plenty of times. So definitely remember this equation and how to do it, determine it, because it'll save a lot of time. All right, so the next one we have is torsion. So torsion is pretty much more of a three-dimensional way of how you're changing your direction. It measures how sharply a curve is being twisted and pulled from a plane. This is going to be denoted as tau. Square looking, got top for this is more of a wavy T. Don't know why it's so hard for me to talk right there. It's going to be equal to, this is going to be a little much, dB hat ds dotted, so this is now dot product with n hat. And remember, dB ds would just be equal to negative dB dt all over ds dt, or velocity dotted with n hat. Now for here, you should get a scalar because you're doing a dot product. So you should get just a number here when you're done with it. No more i's, j's, and k's after this. Because remember, a torsion, which is like a force or like a torque, is a number which is a scalar. It doesn't have really, not force, a torque or a moment. Sorry. Sorry, I'm thinking of work. Sorry, work or a moment kind of doesn't have a direction to it. That's going to be a dot product there. Then the last two we have, and this is where I said to get to it, is the tangential and normal acceleration. So tangential acceleration and normal acceleration. There you go. And I'll rewrite the equation up here. Acceleration equals a. Said I was going to do an plus at. All right. So to get the tangential acceleration, and I say they're vectors, but they're really not vectors. You're getting the magnitude of these things. So you're really getting at, magnitude of at, which is dv dt. Magnitude of the derivative of the magnitude of velocity dt. That's what a sub t is, and because you can't really have a direction for at because it's always changing. It's reference whenever your point moves, your reference plane moves, and then you have a change in direction for all your vectors. So you really got to say that, like, this is really a way to putting it is going to be a sub n magnitude, and we'll say this is a vector. We're going to say the E in direction. So this is now a unit vector. This is the normal direction, plus this is the tangential direction. It's probably a better way of denoting all of this, because you can't really break down a sub t and a sub n as vectors. We really only say what they are as scalars. And so this is pretty much your speeding up and slowing down like time derivative. So it's pretty much acceleration in terms of how fast are you moving is your tangential acceleration. Then your normal acceleration, a sub n, is equal to, you might remember this from physics, it would be the magnitude of velocity squared over rho. So your radius of curvature is rho, so it's velocity squared over r. So so normal acceleration is also centripetal acceleration. And we can also write this as v squared times k, because remember, 1 over rho is k. So that's how you can get each of these individually, but then you can put these together. So you put these in the en and the et direction. So we'll say et is going to be going this direction. So that's a sub t. But in the tangential direction, and then we'll have normal acceleration. Going downward. And the resultant here is actually going to be the acceleration overall. So this is telling you how much because this is pretty much describing a particle that we have right here. So this particle is going to be speeding up in the a sub t direction at this instant, and then it's changing direction depending upon the a sub n quantity. If we had no a sub n, we would just be speeding up or slowing down. If we had only a sub n, so if there was no a sub t, if we only had a sub n, we would be going in a circle. If you remember this from physics, that'd be ac, which is also a sub n. You'd just be going in a circle if you have no tangential acceleration to make you speed up or slow down. If you maintain a constant velocity and you have a sub n, then you would just be rotating in a circle. But we'll have a combination of the two, so we're really going to do something that really isn't a circle if we have both of these. And if you want to get, so say you don't have k, say you don't have rho, but you have a sub t and you have acceleration. Another way for you to get acceleration is by, again, doing the Pythagorean theorem. So you can get a sub n by doing the magnitude of your acceleration squared minus a sub t squared. Because again, this is pretty much like a triangle here. Close enough. To where the resultant a, and label this a of t, has these two different quantities. So these are all the different vector equations you're probably going to have to remember. It's not too terrible. You just gotta have to practice it. I don't know, quiz yourself. If you need all of these, they're online on the Google Drive. That tell you how to do all of this. And I hope this helps you all in your first week of classes. I'm sure seeing all this can be very, make you very anxious. Oh, I've never seen all this stuff before. It's really not that bad. I promise, it's really not that bad. It's just a bunch of equations where you plug and chug. The algebra is intense. I mean, I won't lie to you there. The algebra is pretty intense, but in terms of what you have to comprehend, they're not. I mean, you can understand everything that I've said, or you can just look at the equations, which I think it's a lot more helpful for you in the long run if you really understand what's going on. But if you just need to get to the test, yeah, look at the equations and memorize them. But you can really understand them, then you not really need to memorize them. You can be like, oh, well, that just makes sense. If I need to get the tangential unit vector t hat, oh, I just need to do the unit vector for forward velocity. Or if I need to know the normal vector, then I just need to know the change of my tangential direction with respect to my velocity as a unit vector. And I mean, it doesn't have to, if it doesn't make sense to you, I mean, at least hopefully a lot of this makes sense. But if there's some things that just don't make sense, I mean, go ahead, memorize it, do what you need to do, but really try to understand what's going on here, because it'll be really helpful for the people, especially if you're doing a lot more physics-based classes, like if you're ME, civil, electricals require a lot of vectors sometimes. But that's from what I know. But they'd be really helpful if you really understood what's going on. But if not, anyways, good luck. Try to learn this as best you can. Just practice a lot. Right? Let me know if you have any questions or see any issues with anything that I've said. Comment below. Send me emails. Doesn't matter. Please let me know how I did the video. I would like to, this is my first time kind of doing a non-test review of information, and I want to know if this is really helping you learn or if it's just kind of agonizing to listen to me talk without a need to learn content the day before a test. But yeah, please let me know. Thanks.